This is the brain of my 3D printer's new nervous system. It's a control board from Big Tree Tech called the Manta E3EZ. And this isn't the only change that was made today. I rewired every single part of the printer, from the stepper motors to the can umbilical. The one thing I didn't change in this video is the print head. If you're interested where that came from, check out the video linked in the top right or stick around the channel to see me redesign it. But why? Why go through the hassle of replacing all of the electronics in my printer? Well, first was to simplify my setup and give it a much cleaner look, and the other was to make future add-ons like fans, chamber heaters, anything else like that much easier in the future. Since the Manta allows you to use a CAN network, I could easily use my EBB42 without any extra hats or boards. I also no longer needed to have a power cable to power the Pi, or a USB cable between the Pi and the printer. This is thanks to the Manta boards having two 100-pin connectors allowing you to mount a CM4 directly to the board. Another really cool feature of the board is that you can run the motor section of the board at a different voltage than the rest of the board. For instance, I'm running the board on 24 volts, but I could choose to run the motors up to 56 volts. This is great for setups that demand high torque stepper motors. There's also a built-in SPI pinout to connect an ADXL or any other accelerometer to measure resonances for input shaper. Additionally, there's a ribbon cable connector that allows you to attach a screen. Both of those things I'll be doing in later videos. Finally, since I was using CAN for the tool head, I was left with unused pins for things like fans, thermistors, hot ends, and the entire pinout for the Raspberry Pi. This is going to be great for future projects. Anyway, as you saw in the intro, this upgrade wasn't only functional, but also aesthetically pleasing. I loved the silk screen on the back of the board so much that I didn't just want to cover it up. So I spent loads of time over the holidays tracing out the graphic in Fusion 360. I modeled up this case. It prints without supports, has a snap fit lid as always, has mounting points for a fan, a hole for an antenna, and many other features. And I'm happy to report that the design was perfect on the first try. Anyway, while the case was super cool, it wasn't quite scratching that itch for me. I decided I'd figure out how to light the case up. I ended up buying 1mm thick acrylic sheets that were going to go on the inside of the case to help transmit light through the whole entire graphic. I designed a small bracket to help me cut the acrylic sheets to size. It also had a drill guide to help me make the mounting holes. It wasn't perfect, but I got it to work in the end. I also had a part in the case where you could install an LED strip. I added a WS2812 LED strip. These are addressable RGB lights, and I connected it to the RGB header on the Manta. If you're interested in how to control LEDs with Clipper, or just LEDs in general, let me know down in the comment section. I'd be happy to make videos on both of these topics. I managed to get the LEDs lit, and well, it didn't quite look how I wanted it to. I was expecting just the acrylic to light up, but between that not working and the transparent filament I was using, it just didn't turn out how I wanted it to. After some thought, I decided to sand the acrylic sheet down. I did this to rough up the side I wanted to transmit light through and to polish the sides that I didn't want it leaking out of. If you're familiar with total internal reflection, or light not being able to escape a medium, this is the principle I was applying. I was super excited to see how this was going to change things. And, well, again, it didn't do much of anything except make the graphic even harder to see. But it was still cool, and I'd spent too much time on aesthetics already. This project has been in the works for a few weeks now, and I was ready to move on from it. That takes us to getting the CM4 on the Manta. The first step was to just snap the CM4 into place using the two 100-pin connectors. To ensure the CM4 was protected and got proper cooling, I grabbed a very simple heatsink. After adding some thermal pads to the CPU, RAM, eMMC, and PSU, I used 4 screws to secure the heatsink to the Manta. Next, I flashed the CM4 with Mainsail OS. This can simply be done by adding 3 jumpers and connecting the Manta to your computer with the micro USB cable. You then use RPi boot and the Raspberry Pi imager to flash the OS onto the CM4. If you want a more in-depth tutorial on this, you know what to do. After getting the Pi flashed, I wanted to put the lid of the case together. After adding some heat inserts, I got this 92mm Noctua fan mounted to the case. It does require a DC buck converter to drop the motherboard's voltage from 24 volts to 12 volts, the unfortunate reality of Noctua fans. I'm a bit ahead of myself, but it seems like the fan kept the CM4 and the Manta MCU on the underside of the board where there's no airflow under 33 Celsius through the entirety of a print. This is quite different from my last Pi, frequently peaking at 50 Celsius. The next really cool part of having a CM4 instead of a standard Raspberry Pi is getting to add an antenna. The antenna simply connects to the UFL port on the CM4 and mounts to the lid of the case. It seems like this made an appreciable difference in the Wi-Fi performance of the printer. I can't tell if it's the upgrade from the Raspberry Pi 3 to CM4 or what, but where I had spotty webcam footage at 10 frames per second max, I can now easily get 25 frames per second from the same webcam at 720p, or over 10 FPS at 1080p. The CM4 also seems to be much faster when connecting to it over the web interface after initially powering it up. Now that I had the motherboard up and running and some of the basic configuration prepared, it was time to get the printer ready for its new nervous system. The first step was to strip down the printer of its electronics, as well as a bunch of the bulky enclosures used to house the PSU and motherboard. By the end of disassembly, I was left with a trail of old electronics and pieces of the printer. Now, I have to replace all that. So I got to work wiring up the electronics. I mean, what's a nervous system without the system part? That's just nervous, and no one wants to be nervous. The stepper motors felt particularly challenging because I had no idea how to properly wire them. I do know that stepper motors have wire pairs, each connecting to the same coil in the motor. I used a multimeter to find shorts on the stepper pins indicating a coil. I chose to make black and green a pair, and blue and red a pair. I think that's one of the common colorways for wiring up stepper motors. For the stepper side, I needed these JST PH 2.0 connectors, which I luckily had from some past projects. On the board side, I used the included 4-pin JST XH connectors. This was the tricky part, as I had to decide how to define the pairs. If done incorrectly, the motors would either short to the motherboard, or the motors would rotate in the wrong direction. Again, I'm kind of a pro and had no problem making this work at all. Jokes aside, if you have these issues, you just need to swap the order of the wires. The final wiring I used for the setup is shown here. Let me know if you need any kind of clarification. Next, I wired up the limit switches. These were simple 2-wire connections requiring a 3-pin connector on the printer side and a 2-pin connector on the board side. Then came the CAN wiring. I'd already created the CAN loom in my previous printhead video, but it wasn't long enough, and I did it a little bit wrong. First, you don't want to twist the power wires around the communication wires. This can cause some packet loss in the communication. I originally did this for keeping the wires tidy and for effect. You only want to have the CAN high and CAN lower wires to be twisted. Since the loom wasn't long enough, I just soldered extra wire to the end of all 4 wires and added new connectors to the board side. The days of hanging the wires from spare 550 cord were over. This time I was going to do some cable management. I used some orange PET wire looms and some cloth tape to cover all the wires. If you choose to go the same route on any project, please do this part before adding the connectors. Basically, I had to remove all the connectors for all the wiring I'd done to get the looms over the wires. It definitely took some extra effort, but I'm very pleased with how everything turned out. Finally, I needed to wire up the motherboard to the power supply. Before you do that, make sure you remove all 3 headers you added to the motherboard when flashing the CM4, if you haven't already. If you want to know more about the power supply, then check out my last video. This is actually a great segue to the first thing I don't like about the Manta board. The issue I have with the board is both a pro and a con. It's the fact that the CM4 gets its power from the board and not from a separate power supply. This means that the methods covered in my video on controlling your printer's power aren't going to work. Well, they would, but not without consequence. See, when you cut off the power from a Pi without properly shutting it down, you run the risk of corrupting the files on it. This means we can't control the power from the Pi anymore. If we shut the Pi down, we can't control the power. If we cut the power, the Pi doesn't have time to shut down properly. It's okay though. From now on, I'm just gonna shut the Pi down, then ask ALEXA to turn off my printer. Now I will be reinstalling the Relay V1.2 in the future, but I'm only gonna have it detect shorts and not cut power to the board. Anyways, after getting all the wiring sorted out, I began connecting all the headers to the board. After getting the motors wired up, I added the E3EZ drivers, the namesake of the printer board. These are TMC2209 drivers on the EZ form factor boards from Big Tree Tech. They just slot right in fairly easily and take up minimal space without sacrificing function. The rest of the connections were made, including the antenna and fan. Now that we have all the wiring sorted out, it's time to boot the printer up and see how things go. I powered the printer on and... Alright, cross your fingers. It seems like everything was working. The motherboard fan didn't come on though. I measured the voltages across the input of the buck converter and thought it said 24 volts. It really said 2.4 volts. This led me to replace the relay and resolder everything before realizing I had just connected the fan to the wrong header. Otherwise, it looked like things had been working. After going into the web interface, there were a lot of warnings and startup errors, which is to be expected. After chasing these down and fixing them all, I got to the most frustrating part of this project: initializing the CAN 0 network. I hopefully saved you from this by creating a step-by-step guide on my GitHub, linked in the description. I will be making a more in-depth video on this, so stay tuned. But for now, the heavily abridged version is: flash the Manta board with an SD card, connect the EBB42 to your Pi via USB and flash it with Catapult. Reconnect the EBB42 to the CAN wiring and flash it with Clipper. Finally, configure the CAN nodes in your printer.config file. Also, make sure you have a jumper on the 120 ohm pins on both the EBB42 and Manta. My Manta came with this jumper on it, but somehow I'd been using CAN with the EBB42 without having the 120 ohm jumper on that. Luckily, I caught this and added it. Beats me how I've managed without it. Finally, it was time to test the printer and see if everything was running smoothly. This is where I ran into my stepper motor issues. After configuring that, I did some PID tuning, calibrated the bed mesh, and started a print. Everything seemed to go really well. You're joking. It went so well, in fact, that the printer must have reached relativistic speeds, causing some length contraction on my first benchy. Looks like we have some steps not working the way we want it to. That, or I messed up a single number inside of a 500-line configuration file. You choose. After resolving the issue, I printed 2 more benchies, one in spread cycle mode and one in stealth chop mode. Spread cycle is a mode on the TMC drivers that allows you to print with more torque and at higher speeds. Stealth chop mode, on the other hand, is one that makes the drivers run the motors as quietly as possible. I compared these 2 benchies to the one that I previously printed. In some areas the prints were better, in others it was worse. I wasn't expecting any improvement, so it was nice to see no decrease in print quality. Now I think input shaper is where the improvement is going to come from. This should help both get rid of ghosting and potentially allow me to increase the acceleration of the printer. I'm also planning on adding a small touchscreen to the printer. It's called the TFT35, also by Big Tree Tech. Just a small touchscreen. I'll install Clipper screen on it and be able to monitor my printer if I just look down at it. You may have noticed that the wiring in this video was extra long, and that hints at the future purpose of this 3D printer. So if you have an idea of what that is, let me know down in the comment section. If you're interested in seeing where this printer goes, or just seeing future projects that I work on, then go ahead and subscribe to the channel. I hope you enjoyed the video or got some inspiration from it. I want this channel to be one that inspires people to make their own projects, or makes projects that other people can make that don't require really high-cost tools or a lot of different things. If you like the sound of that and you want to see this channel grow, you can support me by using the Amazon affiliate links down in the description. I've included tools that I use in this video and all the different products I use in this video. Anyway, enough groveling. Thanks for watching. I'll see you in the next one. Bye.